All right, let's dive into the world of extreme performance programming. Now, we're not talking about making your app load a little bit faster. No, this is a world where time itself is measured differently. And to survive, you've got to master the microsecond mindset. And that's not hyperbole, it's a fact. We're talking about a reality where high-frequency traders are capturing opportunities that exist for just millionths of a second. A world where a single microsecond, that's 1/1,000,000th of a second, is the difference between success and total failure. So, to figure out how to win, we've got to understand the battlefield. So, let's get a handle on this. To win here, you first have to really appreciate the scale of the fight. We're not just fighting the clock, we're fighting for every single tick. So what can a computer actually do in 1 microsecond? Well, a modern CPU gets somewhere between, say, 3,000 and 5,000 cycles. That's it. That is your entire budget. Every single instruction, every memory access, it all has to fit inside that tiny, tiny window. And this is where that budget just evaporates. I mean, look at this. Accessing data in the L1 cache, which is right next to the processor, that costs maybe a few cycles. Beautiful. But what if you have to go all the way out to RAM? Boom. Hundreds of cycles are gone, just like that. And a context switch? Forget about it. That can cost thousands of cycles, completely blowing your entire microsecond budget in one single operation. It's insane.
Okay, so knowing our budget is that tight, let's meet the enemies. These are the common coding practices that are basically villains, ambushing your code and just sabotaging your speed at this crazy microscopic scale. And here they are, the usual suspects. Memory allocations, which can steal hundreds of cycles, cache misses, forcing that painfully slow trip out to RAM. System calls. These are basically microsecond suicide. The dreaded context switches we just saw. And finally, branch mispredictions. Because it turns out, modern CPUs absolutely despise surprises. So how do we fight back, right? Well, we start with our most powerful weapon. It's a foundational strategy for winning this whole battle, and it all boils down to one simple but incredibly powerful golden rule. And it is this: you never allocate memory on the hot path. So what's the hot path? It's the critical, most frequently executed part of your code. It's the beating heart of your application, the part that runs millions and millions of times. And in that part of the code, creating new memory on the fly is absolutely forbidden. So this creates a really simple but dramatic before and after comparison. The naive way, the way most of us probably learn to code, is you just ask for memory whenever you need it. But the high-performance systems approach, totally different. You pre-allocate everything you could possibly need right at the very start. Let's just walk through that naive approach, because it's a slow-motion disaster. First, you ask for some memory. Then, oops, you need more space. So the whole system has to stop, find a bigger chunk of memory somewhere else, and then, and this is the absolute killer, it has to copy all of your existing data from the old spot to the new one. Every single step introduces unpredictable delays and totally wasted cycles. And here's the fix. It's so elegant. The systems approach just solves every single one of those problems. You grab all the memory you'll need once, right at the beginning. You process all the data right where it is, no moving it around, and you deliver the results with zero copying. The outcome is predictable, lightning-fast execution, every single time. Okay, so we've got that foundation. Now let's get into some more advanced patterns. And I want you to think of these not as complicated rules, but more like ways to whisper to the CPU, to help it do its job as efficiently as possible. First up is cache optimization. And the source material for this had a fantastic analogy. Going to main memory versus the L1 cache is like a Ferrari racing a horse-drawn carriage. I mean, it's not even a contest, right? So the goal is to structure your data so it's always physically close to the processor, always in that Ferrari lane. Next up, we've got branch prediction. Modern CPUs, they're basically incredible fortune tellers. They try to guess which path your code is going to take at an if statement long before it actually gets there. When they guess right, everything is super fast. But when they guess wrong, the whole assembly line just grinds to a halt and you lose precious time. So the trick here is to write your code to be as predictable as possible, helping the CPU guess correctly every single time. So why does any of this matter, right? Why this intense, almost obsessive battle for millions of a second? Well, let's connect all these technical patterns to their critical real-world impact. In high-frequency trading, these are the techniques that let firms act on market changes that are literally invisible to anyone else. And in real-time audio, this mindset is what prevents those annoying glitches and pops in your music or your calls. It creates a seamless experience because any unpredictable slowdown would be immediately obvious to the human ear.
And all of this brings us to the ultimate rule, the core philosophy of this entire explainer. It turns out that at this scale, predictability actually trumps raw speed. A system that is consistently fast, say it runs at 800 nanoseconds every single time, is way more valuable than one that averages 500 nanoseconds but sometimes spikes to 50 microseconds. Those spikes, those are the killers.
And that leaves us with a final thought to chew on. If the real golden rule is that predictability is more important than just raw speed, what other obvious rules of software development get completely turned on their head when you're operating in this high-speed world? What other assumptions do we have to just throw out the window when we're racing against the microsecond?